This presentation will review the Georgia Standards of Excellence 4NF1 and 4NF2, which focus on extending understanding of fraction equivalence and ordering. 4NF1 states that students will explain why two or more fractions are equivalent by multiplying by a fraction equivalent to 1 and by using visual fraction models. Focus attention on how the number and the size of the parts differ, even though the fractions themselves are the same size. Use this principle to recognize and generate equivalent fractions. 4NF2 states that students will compare two fractions with different numerators and different denominators by using visual fraction models, by creating common denominators or numerators, or by comparing to a benchmark fraction such as 1/2. Students will recognize that comparisons are valid only when the two fractions refer to the same whole. And they will record the results of comparisons with symbols such as greater than, equal to, or less than, and justify the conclusions. First and second grade students begin developing fraction understanding by partitioning shapes into halves, quarters, and thirds. They also explore how the sections can have the same size or area, but not necessarily the same shape. Third grade students expand on that foundation by understanding the meaning of unit fractions with denominators of 2, 3, 4, 6, and 8. In addition to area models, students also begin to use length models and number lines and focus on fractions greater than 1. By using models, third grade students explore equivalent fractions. They then compare fractions with like denominators and like numerators. For more information about the progression of fraction understanding, please view the link to Graham Fletcher's video that appears below this presentation. When exploring fractions in fourth grade, it is important that hands-on models are used to build conceptual understanding before jumping into an algorithm to create like numerators or denominators. As students explore with manipulatives, they naturally begin to see the relationships between the equivalent fractions. For example, in this task, students use fraction strips to find all the different ways to create equivalent fractions with multiple opportunities. After they record the results for each fraction, they make a conclusion and determine a rule for finding equivalent fractions. Instead of introducing an algorithm, students begin to see the pattern on their own. In this pizza party task, students use concrete models to solve a complex problem. Not only were the students able to explore comparing fractions and finding equivalent fractions, they discovered how much more was needed so that each student could have the same amount. The concrete tools and rich discussions provided an opportunity for students to truly understand fractions. In this task from Unit 3 in the Georgia Frameworks, students create multiple equivalent fractions by drawing partitioning lines. Once students begin to see the patterns, they generate equivalent fractions without models. So what fraction do you see on this page?
3/4.
Okay. Can you create an equivalent fraction that would be the same as 3/4?
Yes, ma'am.
So you divided this into what?
Halves.
How many halves do you
2
have?
halves.
Okay. So 3/4 times 2 halves equals
6/8.
Fraction Blackout is a great and interactive game that allows students to race to one whole by coloring equivalent fractions. The game board consists of blank fraction strips that students can color as they draw fraction cards. The goal is to use strategies and try to create more whole units than your partner. In this example, the student drew 1/5. In order to make one whole, the student decided to color in 2/10.
Is 1/5 times 2 halves.
Which is the same as multiplying by a fraction equivalent to 1.
Yeah. And so 1 times 2 equals 2, and 5 times 2 equals 10.
So
I
1/5
get
is the same as
2/10. Yeah.
Pick a card. 3/3. Are you able to color 3/3?
No, but I'm going to color 4/4 because 3/3 is equal to a whole, and so is 4/4.
As students explore equivalent fractions, it is important to incorporate a variety of models. When two separate models are side by side, the equivalence may be easy to see. But in this example, students struggled to see the equivalence. They could easily see that the shaded portion is 3/12. but they had a difficult time understanding that 3/12 is equivalent to 1/4.
So what do you think? Is 1/4 correct?
She's only counting one of the rows, and each one has 1/4 shaded in it. So that's why she's only having 1/4, because she's only counting what's shaded.
What
in
if
each row.
could we draw that same picture and just put them all in one row? Okay, try that. So now that you've put them all in the same row, do you think it's 1/4? You don't?
Once students created visuals and used hands-on manipulatives, they began to see the equivalency.
So how can you prove that 1/4 is equivalent to 3/12?
If you divide the whole into thirds, that would make it 12ths, because you already have these lines in 12.
So how many are shaded of the
3/12ths.
Pattern blocks are another great tool to use as students develop understanding of equivalent fractions. But instead of having the hexagon always represent the whole, students can explore the relationship of each shape to different size wholes.
So if the green is 1, you said the yellow is 6, what would the value of the red be?
3.
And what about the value of blue?
2.
If this green represents 1/2, what would a whole look like?
2.
If the green is 1/2 and the hexagon, yellow, is 6/2 or 3 wholes, what is the value of the red?
3/2.
Or what's another way to say
1
that?
and 1/2.
Right? Okay, what's the value of the blue?
2/2.
2/2, which is the same thing as?
1 whole.
So if this is your whole, what fraction of the shape would the red represent?
1/3.
1/3. Because it takes how many to fill the whole?
3.
As students develop a deeper understanding of fractions and the relationships between the numerators and denominators, they are then able to compare and order fractions. Students can use common denominators, common numerators, benchmark numbers such as 1/2 and 1 whole, as well as creating common denominators or numerators. It is important that tricks are not introduced as a way to compare fractions. The butterfly method takes away from helping students develop number sense and negatively impacts student understanding.
Can you compare 2/5 to 2/3?
Yes.
What is the same about those?
The numerators are the same, but the denominators are different, and 2/5 is less because it has smaller pieces, and 2/3 is greater because it has bigger pieces.
Can you put the appropriate symbol to compare? So let's try comparing fractions that do not have the same numerator or same denominator. What do you notice about 7/8? How far away is it from 1 whole?
1.
1 what?
1/8.
1/8. What about 5/6? How far away is it from being a whole?
1/6.
1/6. Can you show me what 5/6 would look like? Okay, so you took out a piece. Can you show me what 7/8 would look like? So they're both missing one piece. But which fraction is greater, 7/8 or 5/6?
7/8.
And why is it greater?
Because it has a lot of pieces, and this only has a little bit of pieces.
Well, the pieces are bigger, so if you're missing one,
if you miss one, that one is less than, because the 1/6 is a big piece, and you're taking a big piece out.
that's right. Let's compare 2/5 to 1/3 using the number lines. Can you show me where 1/3 would be on the top number
1/3 is
line?
right there.
Okay. And what about 2/5? Where would that be?
Right
Right there.
So using the number lines, which fraction is greater?
None of them.
This
Oh,
one
yes,
is because
it's
it's more it's like right here, but this one is like right here in the middle
So
of
it's
them.
a further distance on the number
Yes,
line?
yes.
It Takes Three to Prove It to Me is a great game that allows students to use a variety of strategies to compare fractions abstractly, representatively, and concretely.
So you have 3/4 compared to 2/3. Which fraction shows more?
Mine, because since his parts are bigger, He's going to be missing a bigger piece than...
So how many pieces does it take to make a whole when you have thirds?
3 pieces.
And how many fourths does it take to make a whole?
4.
Where would your fraction 2/3 go on the number line?
About right here.
Okay. Can you prove it with the tiles?
And it already proves that he has a bigger fraction.
So which one is less? 4/8 or 1/8?
Well, 1/8 because if two fractions have the same denominator, you look at which numerator is the biggest. And since he has 4, 4 is obviously bigger than 1, so he has a bigger
Okay.
fraction.
Well, show me on the number line. Where would 4/8 go on the number line?
Probably right there.
Why'd you put it right in the middle?
Because 4/8 is equal to 1/2.
And where would 1/8 go, do you think? So how do you know that 4/6 is greater than 1/2?
Well, 3/6 is equivalent to half, so I know that 4/6 would be a little bit, just a little bit ahead of half.
As shown in the previous video, students can use a variety of strategies to compare fractions. 4th grade students use benchmark numbers such as 1/2 and 1/2 to order and compare. In the Fill the Bucket task, students sort fraction cards into buckets based on their relationship to benchmark numbers. Throughout the task, the students work collaboratively to correctly place each fraction into the correct bucket. They justified their reasoning based on the relationship between the numerator and denominator. Interactive number lines are another great tool for comparing and ordering fractions. In this task, students place the fractions in order from least to greatest.
Where would 3/8 go? Is it less than 1/2 or greater than 1/2?
Less than 1/2.
And how do you know?
Because half of 8 is 4, and it's bigger than 3.
When ordering fractions, it is important to focus on both fractions less than and greater than 1, including mixed numbers and their placement on a number line. Activities such as the bubblegum task incorporate opportunities for real-world application. 4 friends each chewed a different length of the bubblegum tape. Students discovered who chewed the most, least, and same amount by creating number lines to compare.
So which friend ate the most gum?
Helen.
Helen. How much did she eat?
5, 6.
Okay, who ate the least amount?
Elizabeth.
Yes, Elizabeth. Okay, so we have 3/5 is the smallest. Did anyone eat the same amount?
Carlos and Jamal.
You double the 3 to become a 6, and you double the 4 to become an 8.
So even though this one has more pieces, they have the same amount.
Another great task in the Georgia frameworks is their fair share. Students are going on a field trip in 4 separate vehicles. Students cut the subs into equal shares, but will each vehicle receive the same amount?
The next car has 9 people, but only 6 subs. If we divide them in half, would everybody get an equal portion?
No.
How many halves are there in all if we have 6 subs?
12.
12. So 12 can't be divided evenly with 9. Could we divide them into thirds?
Yes.
How many thirds would we have? 3, 6, 9, 12, 15, 18. Can 18 be divided evenly by 9?
Yeah.
Unit 3 in the frameworks also links to a 3-act task, eating cookies. As students watch the video, they share what they notice and what they wonder.
What's the main question you guys want to have answered?
If the remaining cookies are shared between the 3 girls, will they get the same amount?
As students asked questions, clues were revealed that then enabled them to build replicas of the remaining cookies. After creating equivalent fractions, the students were able to show the amounts that each girl would eat. Below this video, you will find links to several additional online resources. For example, Conceptual Math has a variety of models and tools for comparing and creating equivalent fractions. And the Satisfaction game by Greg Tang allows students to compare fractions using all the different strategies shown in the video.